Welcome to AI Frontiers, where we explore the cutting edge of artificial intelligence research. Today we're examining 17 groundbreaking papers from the computer science artificial intelligence domain, published on June 25, 2025. These aren't just incremental improvements, but paradigm-shifting works that challenge our fundamental assumptions about what AI can do. We'll discover AI systems conducting their own research, privacy vulnerabilities in multi-agent systems, and surprising gaps in advanced models' theory of mind capabilities. Picture this. It's 3 a.m., and somewhere in a research lab, an AI agent is quietly designing the next breakthrough in neural architecture, while another AI system is simultaneously checking whether yesterday's groundbreaking paper can actually be reproduced. No human researchers are involved. AI agents are designing neural architectures autonomously, systems are checking paper reproducibility without human intervention, and machines are literally thinking about thinking itself. The future of science is being written by AI. For AI, yet somehow it's more human than ever before. This scenario isn't science fiction. It's happening right now in laboratories around the world. Today's journey takes us through 17 papers that represent more than incremental improvements. These are paradigm shifts that challenge everything we thought we knew about artificial intelligence. We'll explore AI systems conducting autonomous scientific research, discovering privacy vulnerabilities that could compromise millions of users, and revealing surprising gaps in our most advanced models' ability to understand other minds. By the end of this exploration, you'll have a front-row seat to the future being built in laboratories worldwide, and you might find yourself questioning everything you thought you knew about artificial intelligence. Computer science, artificial intelligence, known in academic circles as CS.AI, represents the computational study of intelligent behavior and the design of systems that can think, learn, and act autonomously. Think of it as the engineering discipline that's trying to build minds from silicon and code. This field sits at a fascinating intersection where computer science meets cognitive psychology, where mathematics encounters philosophy, and where theoretical frameworks collide with practical applications. Imagine CS.AI as a vast digital ecosystem, like a digital rainforest where different species of intelligence are evolving at breakneck speed. You have towering giants like large language models, swift predators like reinforcement learning agents, collaborative species like multi-agent systems, and increasingly the meta-species, AI systems, that are designing and improving other AI systems, creating artificial evolution that's accelerating beyond what any human researcher could achieve working alone. The first major theme emerging from today's research centers on autonomous scientific discovery and research automation. This represents perhaps the most meta-level application of artificial intelligence imaginable, using AI to advance AI itself. Think of it as creating digital scientists that can formulate hypotheses, design experiments, implement solutions, and evaluate results with minimal human intervention. It's like teaching a computer to be curious, to wonder what if, and then to systematically explore those possibilities. Chang and colleagues demonstrate AI conducting end-to-end research with their remarkable work showing systems that can generate over 1,100 newly discovered architectures. The implications are staggering. If we can create AI systems that can conduct research as effectively as human scientists, we could potentially accelerate the pace of discovery across all fields of knowledge, like creating researchers without the limitations of human attention spans, biases, or resource constraints. The second theme revolves around privacy and security in multi-agent systems, and the findings here are deeply troubling. As AI agents become more sophisticated and begin working together in complex environments, questions of trust, confidentiality, and information sharing become critical. Imagine a digital boardroom where AI agents representing different companies must collaborate while keeping proprietary information secret. However, research reveals that state-of-the-art models like GPT-4 misclassify private data as shareable in 25.2% of cases, while CLAUD-2.7-SONNET fails a staggering 43.6% of the time. Even more concerning, during extended conversations, these models disclosed private information in nearly 60% of cases, despite explicit instructions to maintain confidentiality. It's like corporate espionage happening in silicon mines, where your AI assistant might casually mention your medical diagnosis during a conversation with another AI agent, despite being explicitly told to keep that information private. The third theme explores a fascinating paradox in artificial intelligence: theory of mind capabilities. Theory of mind refers to the ability to understand that other agents have beliefs, desires, and intentions that may differ from your own. It's what allows you to predict how someone else might react to a situation or understand when someone is being sarcastic. For AI systems that will increasingly interact with humans and other AI agents, this capability is crucial. Yet researchers discovered something counterintuitive. Newer, more sophisticated reasoning models actually perform worse at understanding other agents' mental states than their older counterparts. It's as if in teaching these systems to become better at logical reasoning, we inadvertently made them less socially intelligent. This finding challenges our assumptions about the linear progression of AI capabilities and suggests that optimization for certain types of reasoning may come at the cost of social understandabilities. It's like teaching a math genius who can solve complex equations but can't read emotions or understand social cues. The key findings from today's research reveal surprising discoveries about AI's current state. First, privacy failures are more severe than expected, with AI systems disclosing private information in 60% of extended conversations despite explicit confidentiality instructions. Second, there's a paradoxical relationship where social intelligence actually decreases as reasoning ability increases in advanced models. Third, collaborative systems like CoMind achieved remarkable success, outperforming 79.2% of human competitors across 4 ongoing Kaggle competitions through effective collaboration, rather than brute force computation. Fourth, compact models can beat massive systems. Researchers developed Paladin Mini with only 3.8 billion parameters that demonstrates highly effective capabilities, proving that efficiency and effectiveness don't always require scale. Finally, AI optimization extends beyond pure performance. Systems can double electric vehicle driver profits while simultaneously supporting electrical grid stability, demonstrating how intelligent systems can optimize both economic and environmental outcomes. For our paper of the day, we're diving deep into Language Modeling by Language Models, by Junyun Chang and colleagues, representing one of the most ambitious attempts yet to create truly autonomous AI research systems. Imagine walking into a research laboratory where no humans are present, yet groundbreaking discoveries are being made around the clock. Computer screens display complex neural network architectures being designed, tested, and refined by AI agents that debate the merits of different approaches, critique each other's proposals, and systematically explore design spaces that would take human researchers years to investigate. This isn't science fiction. It's the reality created by the Genesys system. The system employs multiple AI agents taking on distinct roles. Some focus on ideation, others serve as critics conducting adversarial reviews, while others specialize in implementation. Over 1,100 newly discovered architectures were tested, with more than 1,000 fully verified through pre-training, representing a scale of exploration impossible for human researchers within normal constraints. This work provides proof of concept for autonomous scientific discovery, demonstrating that AI systems can successfully conduct end-to-end research with minimal human intervention. The Genesys innovation centers on what researchers call the ladder of scales, a sophisticated methodology for efficient exploration through systematic testing. Recognizing that computational resources are finite and must be used efficiently, the system tests new designs initially at small scales where training is relatively inexpensive. Only the most promising designs advance to larger scales, eventually reaching hundreds of millions of parameters. At each scale, the computational budget becomes more constrained, forcing the system to be increasingly selective about which designs merit further investigation. Perhaps most significantly, the research revealed that genetic programming approaches were far more effective than direct prompting methods for architecture discovery. When the system used evolutionary principles, creating populations of candidate designs, selecting the best performers and generating new candidates through mutation and crossover operations, it achieved an 86 percentage point improvement in successful design generation compared to simply asking language models to propose new architectures directly. This approach allows for the emergence of truly novel combinations of architectural elements, much like how biological evolution can produce unexpected solutions to environmental challenges, enabling the system to explore design spaces that human researchers may never consider. The results from autonomous AI research are nothing short of remarkable in both quality and quantity. The best designs discovered by Genesys proved highly competitive with established architectures, outperforming well-known models like GPT-2 and Mamba2 on 6 out of 9 common benchmarks. These aren't minor improvements or incremental variations of existing designs. The system discovered genuinely novel architectural principles that human researchers hadn't previously identified. The scale of exploration involved over 1,100 newly discovered architectures, with more than 1,000 fully verified through pre-training, representing a scope that would be impossible for human researchers working within normal time and resource constraints. What's particularly fascinating is how the system handles the creative aspects of research through genuine creativity via systematic exploration. The genetic programming approach allows for the emergence of truly novel combinations of architectural elements, enabling the system to explore design spaces that human researchers might never consider, unconstrained by the cognitive biases and assumptions that inevitably influence human creativity. The system doesn't just generate ideas, it implements them, tests them rigorously, and evaluates their performance using the same standards human researchers would apply. Looking toward the future, we're entering a new phase of AI development, characterized by increasing autonomy, sophistication, and integration across different domains. Think of the current moment like the early days of the Internet, when separate computer networks were just beginning to connect and form the global web we know today. We're witnessing the emergence of interconnected AI systems that can collaborate, critique each other's work, and collectively solve problems that no individual system could handle alone. Rather than AI systems replacing human researchers, we're more likely to see the emergence of hybrid teams where human creativity and intuition are amplified by AI systematic analysis and tireless exploration capabilities. This could lead to an acceleration in scientific discovery across all fields, as AI systems help human researchers explore possibilities they may never have considered. The development of more efficient AI architectures suggests sophisticated AI capabilities will become increasingly accessible to researchers and organizations with limited computational resources, leading to a democratization of AI technology. Perhaps most intriguingly, the autonomous research capabilities demonstrated suggest that AI systems might soon be able to tackle some of the most fundamental questions in science and mathematics, with the potential for AI-driven scientific discovery being virtually limitless. As we conclude today's journey through the cutting edge of AI research, we've witnessed something truly remarkable: the emergence of artificial intelligence systems that can think about thinking, research about research, and discover new ways of discovering. From AI agents that can conduct autonomous scientific research to systems that reveal surprising gaps in our most advanced model social intelligence, today's papers paint a picture of a field in rapid transition. The key insights we've explored: privacy vulnerabilities in multi-agent systems, the counterintuitive relationship between reasoning ability and social intelligence, the potential for AI-human collaboration in research, the effectiveness of compact models, and the possibility of autonomous AI research, collectively suggest that we're entering a new era of artificial intelligence development. These aren't just technical advances. They're glimpses into a future where the boundaries between human and artificial intelligence become increasingly blurred, where machines don't just assist human researchers, but become researchers themselves, and where the pace of scientific discovery accelerates beyond anything we've previously experienced. But here's what makes this moment particularly exciting. We're not just passive observers of this transformation, but active shapers of the future being built. This analysis was synthesized using GPT and Claude Sonnet 4 2050514 for comprehensive research analysis with text-to-speech synthesis powered by Deepgram technology for optimal audio delivery. Image generation was enhanced by Grok AI to create compelling visual representations of the research concepts. Human expert review was conducted to ensure accuracy and clarity of the technical content presented. While every effort has been made to accurately represent the research findings, some oversights may exist in this synthesis. All original research references are provided for verification and further exploration. The integration of multiple AI systems in creating this analysis itself demonstrates the collaborative potential of AI technologies that we've discussed throughout today's episode. Subscribe to AI Frontiers for daily AI research insights, where we break down complex papers into compelling stories and connect cutting-edge research to real-world impact. We're building a community of AI enthusiasts who want to shape the future of artificial intelligence together. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive-preprint-server.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive-preprint-server.org.